Okay guys, in this video we're going to begin to look at the graph of parent log functions. Okay, so specifically what I want to start with is just kind of considering what would have to be true about the graph of y equals log base b of x. And this is in log form. What I want to try to do is rewrite it into exponential form just to kind of assess the situation here. But what you might notice is that when we rewrite this into exponential form, we end up with this phrase or this sentence that says b to the y equals x. And so we say b to the y equals x, or what I'd really be more comfortable writing this is x equals b to the y. And so the thing that I want you to notice is that these mean the same thing, but written in different forms. And the reason why I want to focus on this right here is just that it is the inverse of y equals b to the x. And so the major kind of understanding that helps us to graph log functions, at least at first, is just to understand that it is the inverse of all of our exponential functions base b here. And so that is to say that their domains and ranges are going to be switched, their behaviors are going to be switched, and also it's going to be reflected over this line y equals x, okay, from the graph of y equals b to the x. So when we graph y equals log base b of x, it's just going to be a reflection over the line y equals x of the graph of y equals b to the x here. So in order to kind of get an idea of what this looks like here, I'm going to have us complete the table for the function y equals 2 to the x. So we're going to look at the graph of an exponential function and then kind of use that table to sketch the graph of y equals log base 2 of x, which would be the exact inverse of y equals 2 to the x. Okay. So generally speaking, we would say, and I want to make sure we write this here, y equals log base b of x is the inverse of y equals 2 to the x. The exponential function with a base of 2 is the inverse of the logarithmic function with a base of 2. And this should be a 2. Sorry, 2. So when we look at this right here, I suppose that we want to complete this table. Well, this is for 2 to the x power. So we say 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the negative 1 is the reciprocal of 2 to the positive 1, and 2 to the negative 2 is the reciprocal of 2 to the positive 2. So with respect to our parent exponential function, these are pretty easy just because the asymptote is always the x-axis. Tends to go through 0, 1, and in this case goes through 1, 2, and 2, 4. Negative 1 1/2, negative 2 1/4. So I'm going to sketch this in. We say, okay, here is our exponential function with a base of 2. This is our y equals 2 to the x. Now what I want to do is graph its inverse. And so we're going to make a new table here. I am going to switch colors. I'm going to switch to a vertical table just because the horizontal ones drive me crazy. So we're going to say x and y equals log base 2 of x. So now the neat thing about this is, at least for right now, what I want to make sure you do is just go ahead and let's plug in for our x values the original y values of the original function. So we're going to plug these in here. So we get 1, 2, and 4. And what we get out of it are the original inputs. So negative 2, negative 1, 0, 1, and 2. Those become our outputs on this function just because these two tables swap their values, or domains and ranges swap. So what I want to do is I just want to kind of take a look at what these points would kind of look like if we graphed them. And so I know that if I go right 1/4 and down 2, I'd be about right here. If I go right 1/2 and down 1, I'd be about right here. If I go right 1, I'd go up and down none, so that'd be this point right here. Right 2 up 1, and then right 4 up 2. That'd be this point right here. So what I can see already is that this function is reflected over this line y equals x from the original function, and that these are inverses of one another. The other thing with inverses, though, is that their domains and ranges switch. And so I know that as I look at the original one here, its domain happens to be negative infinity to infinity, and it looks like its range is just above 0 to infinity. The thing here is the opposite is going to be true for our domain and range on our logarithmic graph. So its range is going to be all real y values, but its domain is only going to be positive x values here. So as I look at the domain, the thing I want to kind of basically point out is that if it's only positive x values, then it's only going to open to the right here. And so whereas the, I suppose, exponential graphs all have a horizontal asymptote, and they all, on their parent function at least, is on the x-axis, all logarithmic graphs have a vertical asymptote, and it, on the parent function, occurs by default on the y-axis here. So x equals 0. And we get this graph that just kind of creeps up really fast at first and always increases, but does so more slowly and more slowly. So if I were to describe what's happening with our exponential graph here, it's always increasing, but it's speeding up and speeding up and speeding up. It's getting a steeper and steeper and steeper slope, whereas a logarithmic graph, it looks like it's always increasing also, but it starts off speeding up super fast, whereas the other ones start off speeding or increasing very slowly. This one increases very quickly, but then changes its mind and always increases, but increases more and more slowly, whereas an exponential graph increases more and more quickly here. And so what I want to kind of take a look at is, well, what would I want to know about my logarithmic parent function? I would want to know that there is an asymptote on the y-axis. Instead of going through the point 0, 1, which is pretty common, we're going to go through 1, 0. And in terms of what points I would want to table, I would want to table probably these points right here that I see right here. Okay. So we are going to take a look at the logarithmic parent function and just say, if I know what this parent function looks like, then maybe what I can hope to do is start to transform them next. So determine the following for a graph of the form y equals log base b of x. The very first thing that I want you to recognize is that all logarithmic functions, at least a parent function that hasn't been transformed, is going to have a vertical asymptote at x equals 0, or in other words, on the y-axis. And an easy way to remember this is just that logarithmic functions behave as inverses to exponential functions. So if exponential functions all have their asymptotes on the x-axis, this one has it on the y-axis. Now in terms of tabling values, I will tell you that we can table any x value we want, so long as the x value that we plug into this log comes out to be a positive. But in terms of which ones we tend to table very, very convenient values. And so what I'm going to tell you is, because it's the inverse of something that is exponential like this, okay, I'm going to plug in the original outputs of an exponential thing as the inputs for a logarithmic thing. So you're going to notice that on this one here, I use the inputs 1/2, 1, and 2, but this was a log base 2 kind of a thing. So why did I use 1/2, 1, and 2? I think it's easy to find out what could I take 2 to the power of to get 2, and I think it's easy to find out what could I take 2 to the power of to get a half. I also think it's easy to take the log of 1, and this is all just very true because of our properties of logarithms that we looked at. The log of 1 is 0. So when we look at this graph right here, what I want you to always know is that when we table values, we're always going to table 1 for a log parent function, the base for the next input, and the one before 1, we're going to put in 1 over the base. And I actually want to take the time to evaluate these here. And so what we would get here is log base b of 1 over b, which, if we consider this here, what could we take b to the power of to get 1 over b? It would have to be negative 1. What if we do log base b of 1? What could I take b to the power of to get 1? It would have to be 0. And what could I take b to the power of to get b? If I plug b in for x into this function here, log base b of b would always be 1. So as long as we are using 1 and then the base and the reciprocal of the base, we always get these kind of 3 outputs right here. The only difference then is going to be what is the base. So some things. The very first one I want you to put on is just make sure that you acknowledge that for a parent log function, it's always going to have the point 1, 0. And in terms of what other points I'm going to put on here, I'm just going to say that this right here is b, that x value. I'm choosing an arbitrary x value, but I know at b, it's going to be at a height of 1. And then the reciprocal of b would have to be between 0 and 1, maybe like right here. This is like maybe 1 over b, right there. But this would have to be at a height of negative 1. And so we always kind of get these logarithmic graphs that just look like this right here, okay? And that would be an adequate shape enough for me. So in terms of domain, let's write a few things here. Any log parent function is going to have a domain of 0 to infinity and a range of negative infinity to infinity, which is worth noting is the exact inverse of what we see with exponential functions, okay? And in terms of x-intercept, we would just want to acknowledge that it always goes through 1, 0. Lastly, is it always increasing or decreasing? Logarithmic parent functions are always increasing. We're talking about the parent function there. So, important things. There's a vertical asymptote at x equals 0. There's an intercept at 1, 0. And we always table kind of these 3 values here. So as we look at maybe graphing a couple of transformations of this now, what I would say is we can still go and graph the transformations of this, but we kind of need to know what the parent function looks like first. So taking a look at these two here, it says, do me a favor, use the graph of the parent function to sketch the following transformations. Be sure to label the asymptote of the graph as well as any points on the graph, and then state the domain and range. So first things first, if we were to graph, say, the parent function here, what would it look like? And so I am going to table this, as a matter of fact. I'm going to say x, I'm going to say y equals log base 10 of x. In other words, I'm going to graph the parent function as if this h value doesn't exist and we don't have a k value, and our a value is already 1. So in terms of what I plug in, okay, I hope you were paying attention. We always plug in 1 in the middle and then 1 over b and b respectively around the 1. So we're going to plug in 1. We're also going to plug in the base. Well, our base this time is 10, and our reciprocal of our base is 1 over 10. So in terms of evaluating for just our parent function here, what would be the log of 1? The log of 1 would be 0. How about the log base 10 of 10? Well, that would be 1. And how about the log base 10 of 1 over 10? That would be negative 1. Okay. So to graph our parent function here, it would have an asymptote that lies on the y-axis. We're going to label that x equals 0. And then we're going to draw in our points that we need to graph here. So 1/10 comma negative 1, 1, 0, and then we got to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the right and 1 up. You can see that this graph here looks just like our parent logarithmic function, except for it grows really slowly. It's because we have a big base there. So in terms of this graph here, how would I find now the new graph of log base 10 of x plus 4, the common log of x plus 4? I recognize that this plus 4 here is an h value, and then it's going to shift left 4 units from the parent function. And so we're just going to pick everything up here, including the asymptote 1, 2, 3, 4, and we are going to move everybody left 4 units. And so this becomes x equals negative 4. And in terms of our points, we got 1, 2, 3, 4. That would be right here. This point here would be here. And then this point that was at 10 comma 1 would now be at, I suppose, moving it 4 units to the left, 9, 8, 7, 6 comma 1 would be right here. Here would be the graph of this logarithmic function right here. So in terms of what do I want to state here? Well, I want to state the domain and range, and I mean of the transformed graph. So its domain is going to be negative 4 to infinity, and its range looks like it goes from negative infinity to infinity. And this is true for all logarithmic graphs. Its range will always be negative to positive infinity. So let's take a look at this letter b here, g of x. If I wanted to go graph log base 3 of x plus 2, you might already be foreshadowing a little bit here. Hey, this is just going to be our parent function shifted up 3. So let's go ahead and do the same thing we did previously, which is we're going to table some values for our parent function, which is log, this time, base 3 of x. And so in terms of what we plug in, remember we put 1 in the middle, but we always put the base and 1 over the base as our other inputs because they're convenient. So when we say, well, what is log base 3 of 1? We should get 0. How about log base 3 of 3? Well, what can I take 3 to the power to get 3? That's 1. And then log base 3 of 1 over 3, that would have to be a negative 1 power here. So at least for our parent function, let's again put our automatic 100% of the time by default asymptote on the y-axis. We're going to label this x equals 0. Now this is for our parent function that goes through 1, 0, 3, 1, and 1/3 comma negative 1. So you can see that this is really, just looks like our parent function for our common log we did on the last problem there, except for it's just not as flat. So shifting these, it looks like our shift this time is a shift up 2. So if I shift everybody up 2, this is now at a height of 2. This one was at a height of 1, now it's at a height of 3. This was at a height of negative 1, now it's at a height of positive 1. We get this new graph that looks like our original parent function. It just is shifted up 2. And so as far as its domain and range go here, you can notice that the domain is 0 to infinity. Just like on the parent function, the domain was 0 to infinity. So why didn't it switch? Well, the thing here is this: we shifted our graph up, which does shift our asymptote up, but it's a vertical asymptote, so it really doesn't affect where the domain lies. And then our last thing we want to list is the range. But hey, it's always good to keep in mind that any log graph is going to have a range of negative infinity to infinity. Cheers.